A discrete random variable is a random variable where the values are discrete and we can assign probabilities associated to those individual values. The function that measures those probabilities is the probability distribution or probability mass function. So imagine we have a random variable. An example might be a binomial distribution. So let's do something like binomial, 4 attempts, and probability is 1/4. Alright, so we can calculate the probabilities of individual values. So x has 5 possible values. It could be a 0, a 1, a 2, a 3, or a 4. And now we'll calculate those 5 probabilities. For example, to calculate the probability that x equals 0, the binomial distribution says we take 4, choose 0, and then we multiply 1/4 raised to the power of how many x's we got, 0, and then 3/4 times the power of how many we did not get, which this time is 4. So the probability that x equals 0 is 81 out of 256, or 0.3164 approximately. In a similar way, we can calculate the probability that x equals 1, x equals 2, x equals 3, or x equals 4 using the same basic formula, substituting in 1, 2, 3, or 4 in the location of our value. In fact, that's the whole purpose of the probability distribution function or mass function. The formula is exactly what it means. You take 4, choose the number of values that you say the variable is, 1/4 to that power, and 3/4 to the 4 minus that power. And this is the probability mass function, or the probability distribution function. Now if I had the experiment and I actually did the experiment, any individual result would give me just one of the 5 values, 0, 1, 2, 3, or 4. The probabilities, what they represent is if I were to replicate the experiment many, many times, the probabilities I just calculated would represent the relative frequencies, or approximate the relative frequencies that I would see. Alright, so I implemented this particular example we did, and I did this in R 1,000 times, and I calculated how many times I saw a 0, and out of the 1,000 I saw 0 301 times. The number of times I found of 1 was 434. The number of times I saw a 2 was 214. The number of times I saw a 3 was 46. And the number of times I saw 4 was 5. Alright, so if I were to calculate the relative frequency out of 1,000 tries, I would simply divide the 301 by 1,000, and I would see an observed value of 0.301. For a 1, my probability would have been occurring with 0.434. The probability of a 2 would have been 0.214. The probability of a 3 would have been 0.4046, and the probability of a 5 would have been 0.005. Now these aren't probabilities in the same sense as the binomial probability distribution function. These are relative frequencies. 301 out of the 1,000 times I saw a 0, 434 times out of 1,000 I saw a 1, and so on. And you should be able to see that these probabilities that I'm measuring through relative frequency are very close to the probabilities that are predicted using the theory. Now, if I were to take my 1,000 tries and calculate my average, then I would have been adding all these up, dividing it by 1,000 to see what my average value was. And so my average would be, well, I have 0 301 times. So it's 0 301 times. Put in parentheses. And then I had a 1 434 times. And I had a 2 214 times. and I had a 3 46 times. And I had a 4 5 times. And if I were to add all those up and divide it by 1,000, I would calculate my sample mean. This is the regular average, the kind of average that we might normally think about. And when I add all those values together and divide it by 1,000, adding them together I get 1,020. Dividing by 1,000, I get 1.02. And that's my sample mean. So if I were to add the 5 numbers together, 0 plus 1 plus 2 plus 3 plus 4, and divide it by 5, I get something completely different and fairly far away from the sample average. So what is it that's going to calculate the average theoretically? Well, this is where we get to expected value. So expected value is calculated as a weighted average, where instead of adding up the numbers 0, 1, 2, 3, and 4, we multiply the value times its probability, and that's what I add up. So 0 appears 81 out of 256 times. 1 appears 108 out of 256 times. 2 appears 54 out of 256 times. 3 appears 12 out of 256 times. And 4 appears at once every 256 times. And those are all averages, so this is something that's being said about what we expect, what would happen in a very large sample. So for notation, we write the expected value of x. We take the random variable x, we take its values 0, 1, 2, 3, and 4, we multiply them by their probabilities, 81 out of 256, 108 out of 256, 54 out of 256, 12 out of 256, and 1 out of 256. I multiply those and add them up. And so I get a new fraction. I get out of 256, I get 0 plus 108. And when I multiply 2 times 54, I get another 108. I then add 36 from 3 times 12 and 4. And when you add all those together, you get a sum. The total is 256 over 256. That is, our expected value of x is the number 1. And if you compare that to the sample mean that we calculated in the last example, it was really, really close to 1. I think it was 1.02. So the expected value is the value that is the appropriate estimation for the sample average if I were to do the theoretical calculation. Now this idea extends to other functions of the random variable. For example, if I'm interested in x squared, the value of x squared, when x is 0, x squared is 0. When x is 1, x squared is 1. When x is 2, x squared is 4. When x is 3, x squared is 9. And when x is 4, x squared is 16. However, the probabilities are the same as before. The probability of 0, 1, 2, 3, and 4 are unchanged. If I'm interested in the expected value of x squared, then what I will get is I'm going to get 0, that's the first value of the x squared table, times the probability that I see in x squared equals 0, plus 1, that's 1 squared, times the probability that I expect to see that, plus 4, that's 2 squared, times the probability I get a 2, plus 9, that's 3 squared, the probability I get a 3, plus 16, that's 4 squared, times the probability that I would see a 4. And so the expected value of x squared is the sum of 0 times the probability of 0 plus 1 times the probability of 1 plus 4 times the probability I see that plus 9 times the probability I see that plus 16 times the probability I see that. But the probability is coming from the original random variable. And when I add all those values together, I get 0 plus 108 plus 216 plus 108 plus 16 divided by 256 for a grand total of 448 out of 256. And that's the expected value of x squared. So this allows us to generalize it. If I have some other function, let's call it g of x, then there are 5 values. There's the g of 0 value, there's the g of 1 value, there's the g of 2 value, there's the g of 3 value, and the g of 4 value. Sorry, those g's look like y's. But what I would do is I'd take each of those values, the g of 0, multiply it by its probability I see a 0, g of 1, probability I see a 1, g of 2, the probability I see a 2, g of 3, the probability I see a 3, g4, the probability I see a 4, and I add those all up. And that would be the expected value of g of my random variable. And so this is how we calculate expected values. If I have a formula, I would write it with summation notation. I sum over all values of x the value of my observed function, g of x, times the probability I see the value of x. And I go over the entire state space. For our problem, my x's went from 0 to 4. But in general, they would go through whatever the range of possible values are for my random variable x. This is the definition of expected value. And that's how it's calculated for discrete random variables. For multivariate random variables, it works in a similar way, except now we have a joint distribution function. So if I have a pair xy, then the probability of that point, you take the x value, 4 minus y, you multiply those and divide by 20, and this will be the probability of an individual point. So for example, the point 1, 3, x is 1, y is 3, so it's 1 times 1 over 20. And so the probability of that point is 1 out of 20. So expected value is going to work in a similar way. If I have any function of x, y, then I can calculate an expected value. So for example, if I'm interested in the function x, then for each of the 5 points, I can calculate the value of x. It's 1 for the first 2 points, 2 for the third point, and 3 for the last 2 points. And so if I want to calculate an expected value, I would take those values times their probabilities. 1 times 3/20, 1 times 1/20, 2 times 4/20, better slow down, 3 times 9/20, and 3 times 3/20. And I add all those up, which equals a total of 48/20. So that's 12/5, or 2.4. And so we calculate expected values that way. We can also calculate an expected value of y in a similar way, except instead of using the x values, I'd use the y values. So I can also calculate expected values of functions involving both variables. So for example, I could think about the function x times y. So the point 1, 1, the product is 1. The point 1, 3, the product is 3. The point 2, 2, the product is 4. 3, 1 gives me 3, and 3, 3 gives me 9. And so if I want to calculate the expected value of xy, I'll take 1 times 3/20 plus the next product 3 times 1/20, the next product 4 times 4/20, the product 3 times the probability 9/20, and the last product 9 times the probability 3/20, which gives me a grand total of 76/20. So this is how expected value works. You take the value times the probability, and you add up all those results, and that's your expected value.